My name is Jonah Flint, and this is my Physics 2211 Lab 4 report on oscillation. For our introduction and purpose, as well as our findings, in this lab we are attempting to record and track the motion of an oscillating vertical spring and mass system with both x and y components of the translational motion. And then we're going to use our knowledge of forces and the work-energy theorem, as well as some fundamental principles, to model this motion in GlowScript and then compare the tracker model with our modeled motion. And a quick overview of our findings, we found that the motion recorded and predicted were very similar, but there was some greater similarity in the x direction than in the y. And we also found that the change in energy of the system was 0. This is assuming that there's no air resistance and friction. Some key concepts, we need to know Newton's second law and the momentum principle here. And then we're going to also use the position and velocity update formulas. And then we're going to use the energy principle a lot in our calculations, which is just stating that the change in energy of the system is equal to the work done by the surroundings plus thermal energy. And here we have the equations for kinetic, gravitational potential, and spring potential energies, and a quick diagram of what equilibrium looks like for forces. For our tracker model, we have a string length initially of 0.7 meters, and that is what I used to calibrate this video. And the initial position of the mass was negative 0.123, comma negative 0.657 meters, and the initial time was 0.475 seconds. This is because the oscillating motion rather, starts actually on the 5th frame of the video. Now for the first part of our GlowScript model. First of all, over here we are using the values from the pre-lecture video to calculate the spring constant, which was found to be 6.83, and we use the L0 value here to find that. And then we are calculating the energies in the system using these equations here. And then we're going to use these equations down here to calculate the forces and thus the net forces on the system. In our second part here, we are first calculating the changes in energy. We're again using those kinetic energy, gravitational potential, and spring potential energies to find the delta K, delta UG, and delta US values. And then we can take those and find the total change in energy of our system, which we will show later. And down here, this is just the code for the visualizers. And now onto our findings. Up here we have our graph of all of our energies. Blue is the kinetic energy, red is the gravitational potential, green is the spring potential, and importantly, orange down here is the total change of energy in the system. Notice that it is 0. And also, interestingly to note, the delta U spring and delta U gravitational are equal in magnitude, but inverse in amplitude here, or not amplitude, they're shifted off from one another. Some possible sources of error in our finding are air resistance, friction, subhuman error, thermal dissipation, and possible tracker error. And note down here, again, as mentioned before, our x position modeled and experimental data matched a little bit better than our y position data. Conclusions. Is the energy principle satisfied? Yes, it is. Going back to that orange line here being flat, thus the change in total energy of the system was 0. This is again assuming that there was no work done by the surroundings and 0 thermal loss. And this was just again the change in kinetic energy combined with the change in gravitational potential and change in spring potential energies. And then for the second part of this question here, when we are asked to find the periods of oscillation in both the x and y directions, I calculated this to be 0.152 seconds in the y direction, and right here, and 0.164 seconds in the x direction. And this was just taken by the average of these distances between the peaks here. And this has a couple of big impacts on the spring force and the spring constant calculations from before. And it could also greatly affect the spring potential energy calculations. And some possible sources of error in these calculations could again be from air resistance or friction, some error in the tracker model, and some possible human error in the actual experiment.